Hi, this is Richard Collins. This is the second video, but I'm going to send it to you first because I made a tired mistake when I was showing you the earlier video. Everything in there is valid up to about the last few minutes, and this is the correct way to go about it. The sun components of the vector are these. The moon component are these. And in each case, this is the sun's acceleration at the station minus the sun's acceleration at the center of the Earth. And that's the x component of it. This is the y component of the sun's acceleration at the station minus the sun's acceleration at the center of the Earth. So these are the three components of the sun portion of the differential gravity signal at the station. These are the three components of the moon's acceleration at the station minus the moon's acceleration at the center of the Earth. Now, simply vectorially adding these together gives you this result, and then the sum of squares, the magnitude of that, gives you the correct magnitude. I was doing a very stupid thing. I was adding up the sun and moon magnitudes and comparing them to this, and that was totally off the wall. Sorry, I'm just my health is not great these days. Anyway, so I will send this along as an addendum, which I'm going to ask you to watch first so that you will know. And just to give you the context for this one, I got the raw data, here, x, y, and z, x dot, y dot, z dot for the sun, the light time from the sun to the station, the distance from the sun to the station, the rate of change in distance from the station to the sun, the corresponding x, y, and z station coordinates of the moon, the rate of change of each of those coordinates, the light time from the station to the moon, the distance from the station to the moon, and the rate of change of the distance to the moon. I can see that I've got mixed notation in here a little bit. Hopefully you can use it. And then these are the coordinates for the center of the Earth from the station, the rate of change of the location, of the rate of change of the station, the rate of change of the distance from the station to the center of the Earth, the light time, the distance from the station to the center of the Earth, and the rate of change of the distance. From those, I extracted just the x, y, z, and distance from that table, and put it in here. So I got the x, y, and z and distance for the sun, for the moon, and the Earth. From that, I can calculate also the distance from the sun to the center of the Earth, from the moon to the center of the Earth. I use that in a calculation of the sun's component of acceleration at the station minus the sun's acceleration at the center of the earth, the moon's acceleration of the station minus the moon's acceleration at the center of the earth. And then I multiply that into the unit vectors in the sun's direction and in the moon's direction, add those two vectors to get the differential acceleration at the station in station coordinates of the gravity signal. And then this is the magnitude of the gravity signal. So these three here, this shows you what you can expect at the station. The Z component is along the Earth's north pole direction. The X and Y components are along the equator. And at the moment, my brain will not tell me exactly the coordinates, there. I'll have to look to figure out the time. The times are in the table, so you know precisely Julian date and time. These are steps in minutes. I just did a simple minute calculation. So these are minute by minute from October 1st, 2016 to October 9th, 2016. So just 8 days worth of information. So I like to be complete and keep looking at things. So this is the moon's contribution, and I don't know the specific geometry of the orbits at the time. I have to go back and check them methodically to be sure I get them right. But this is a simple plot of the moon's contribution to the gravity signal, and this is the sun's. If we can get to the point where we have 3-axis gravimeter arrays, each individual gravimeter, once it's calibrated, can be inverted. The data can be inverted to tell you this portion. If you say that I know the moon's contribution, you can solve for the sun's contribution. Do you understand what I'm saying? Let me repeat that. If I measure and calibrate a 3-axis gravimeter, and I detect a total signal like this, if I keep the moon's contribution constant, that is at its nominal values that everyone agrees on, then I can solve for the sun's component. Since I know the magnitudes in here, I can invert this and actually solve for the distance to the sun, and these would be the 3 components of its position. Likewise, if I get measured components of the total signal from the instrument, I hold the sun constant, which is actually even more reasonable, then I can solve for the moon's position, mass, and distance. So each of these things, they're all tied together. It's a network of interrelated constants, if you like, through mathematical models. And you can back solve and hold constant what you please in a fairly simple framework. So what I'm trying to do here is to I'd like to be able to do this simple problem. Okay, it's a really trivial problem. High school vector calculus, first year college physics kind of problem that anyone can do. I mean, they can go to Horizon. That other video will show you. You can go to Horizon, generate this table, get your vectors, and you'll know what the signal is. With this, you can calibrate a superconducting gravimeter, a seismometer, an atomic interferometer, atomic interferometric gravimeter, any MEMS gravimeter, whatever setup you have, you can relate it to this. So if you have a plate hanging somewhere and it's facing east and west, then it will see the east and west signals like this, and the second derivative of the position of this. So if you take the center of mass of your plate and follow its position, the small variations of its position will correspond, the second derivative of its position will match this signal, okay? And it'll match probably within an offset and a multiplier. So you simply add a scale factor and multiply by a scaling factor to get them to match. Now, at worst, if your hinge on the plate is nonlinear for some reason, then you'll need to do another sort of transformation in there and all. So you may find, like when this is large, that you need to scale. So you may need a nonlinear scale factor. I'd like to actually solve some of those problems if people would let me see the actual data from the experiments. It's no more tedious than this. I mean, if you actually do these calculations from the Chebyshev polynomials and you do it sort of from scratch like that, it can be it's tedious is my word for it. It takes a lot of checking, verification, cross-checking, retesting, re-examining. It's an almost endless process, but the end result of it is just really elegantly simple. If we look at those, if we look at the actual data in here, this is a superconducting vertical signal. Okay, superconducting gravimeter vertical signal. The blue, which you can't even see in here, it's just slightly out of whack in here. So you can just, if you could zoom in really far, you would see tiny little bits of blue here showing. So in fact, let me do this. I'm going to delete this calculated value, and there underneath is the round. So if I undo this, so there, that orange is the calculated value after scaling the gravity, the true gravity signal. Then this is the signal from the instrument. So what I would like to do is to flip this over. I took the gravity signal and modified it to reproduce the instrument signal. What we really need to do is to do it the other way. Take the calibration numbers that I produced here and have the instrument report the true gravity signal. If everyone uses, like a seismometer reports gravity signal units, if they can report what the sun and moon signal looks like, then you're working with common units throughout. This is instrument units. This is this particular Wuhan December 97 instrument, which actually could change over time. So if you do that, I think we would be better off. So rather than anyway, it's I think it's extremely elegant. I did not think that GMM over R square worked on this scale. It's when I first approached this, I went through all the Earth models and I tried to figure what do they call, spherical harmonic expansions of everything, and it was a total mess. I spent probably 6 months suffering, trying to understand every dynamic of the Earth and all, until I finally said, do I really need to do that? Maybe the gravity, does work directly there at the station that way, just like we do in Cavendish experiment. The gravity of the sun acts GMM over R squared on the mass inside the gravimeter, and then it acts on the center of the Earth, on the Earth as a whole. And the difference between those is its contribution to the acceleration that we measure. And the moon does the same thing. And because vectors just add nicely, independently, you get the total signal, the contributions from the sun and moon added nicely. This is a pretty good demonstration. Now, I know that I'm not satisfied with this. This is a 0.9998 R squared. I'm not satisfied with that ultimately. I just cut out on this December segment, I just cut out the noisy times because there were spikes on either side of this. I would like to see, I'd like to see us push this out so this reads 999 out to 16 digits. There's no reason we can't do that these days. We have to use full precision calculations. We have to understand and calibrate our machines better. We use a lot of numbers, but technically there's nothing that stands in the way of using all of these extremely precise instruments as a single instrument. So as the VLBI people do, and the radio astronomy and now optical interferometry astronomy, all of the techniques that are being used for global scale astronomy could be done with gravimetry as well. So I'm putting in a plea for people to move in this direction. At least, please, someone build a 3-axis gravimeter so we can at least do this simple thing. Calculate the sun's position holding the moon constant. Calculate the moon's position holding the sun constant. I think it will lead to very, very interesting things. At the very least, this is something a high school student can understand, okay? And it might give them an idea about the dynamics and wonder of gravimetry and such a direct thing. Okay, I got a minute here. I'm going to say one last thing. I could not understand. I actually started this partly because I wanted to see if I could measure the speed of gravity. There was a bunch of hullabaloo about it, that, oh, yes, gravity moves at a certain speed. These are instantaneous gravity signals. They're based on the instantaneous position of the sun, the moon, and the earth. There is no light, there is no gravity time involved. And the way after it's quite a few years, decades now, that I've been thinking about this, I finally think I understand that there are two parts to gravity. There is the Newtonian gravity, which is the culmination of all the individual processes that bring gravity to a given place. So if you like, the energy density, the gravitational potential at a point in the solar system or anywhere in the universe is the sum or the culmination of all of the events that made that point. So it reflects the kind of the norm for that position. So when you're at the station, you're seeing the station's gravity at equilibrium. Okay, now suppose that a giant flare shows up on the sun. That signal will move from the sun to the earth at the speed of light, as far as I know. I mean, that seems to be the way it works. Then this network should eventually be sensitive enough to measure the sun's variations in mass distribution at the earth. I don't know the mathematics, frankly, myself at this point. I don't know if I'll survive long enough to see that, but I do believe that you can see that. Like as well, internal mass distributions and shape changes of the Earth should also be accessible here, and particularly, I think that the people who are interested in the shape and dynamics of the Earth could use a global network of these that can image the interior of the Earth. Maybe I'm pushing this beyond what's possible. I understand the gravity gradiometry that's used in the satellite measurements of the Earth's interior, its Earth's gravity field, and that's now a dynamic reported result, and it's useful, but I can't formulate my worry about that in a sense. It's not a well. Let me stop. I wanted to keep this as technical as possible, but I did feel like I could give you an idea why I have been doing this for so long. This needs correction for you have to worry about the centrifugal force at the station for the vertical. You have to worry about the earth tides. You have to worry about the acceleration about the Earth-Moon barycenter, which I think may be the problem in that other in here. These small misses in here. I think those are so consistent and so smooth that they're very likely just that. I think that it's about the right order of magnitude, and I think that might be why. So I ran from 2003 to 2013. I ran about a decade of all the superconducting gravimeters. I ran a number of broadband seismometers. The seismometers are so massive an undertaking. I don't remember how many seismometer models I had to go through before I found the ones where I could extract this signal. But it's there, and it's a good means of calibrating, because all you're looking for is an offset and a multiplier. And that sets the scale for that instrument from that point on. You can also, if it's a 3-axis instrument, like a seismometer, 3-axis, you can use that to calibrate the orientation of the device continuously. So, for instance, if you have a 3-axis seismometer that's sensitive enough to see the sun-moon gravity signal, then you can solve for its orientation in 3-dimensional space, and quite precisely. You can do that once an hour, once a day, maybe every few minutes. It depends on your data rate, your sampling rate. Okay, this is getting long again. So we've gone a long way from horizon to the components of the gravity signal. Please ask questions if this is of interest to you at all. Thank you.